The first time I billed hours to the Bay Bridge job was 1998. And then there was a 7-year hiatus when that whole suspension bridge design was put on the shelf and it looked like it wasn't going to be built. But there were a lot of political disagreements, but finally in 2006, the construction started. And so I spent about a year on the design back in 98, 99, and then on construction since 06. So I've also worked on anything from overpasses. I've worked on, there's this light rail, like elevated structure that we did in Monterey, Mexico. That was a couple of kilometers long. Let's see, I've done cable inspections of suspension bridges. So I've spent maybe in my career, I've spent about a quarter of my time outdoors and 3/4 indoors. So that's what I like about the profession, the fact that I can go outside or go to a site visit and be working, but also be outside and see the results of what we're working on in the office. What I also like is that as a civil and structural engineer, what you're designing and building isn't going to be obsolete in 3 years. My phone is going to be obsolete in 3 years, but the Bay Bridge is going to be around in 200 years. So that's an appeal of the profession for me. Okay, I guess I don't know how clear this is. Maybe we can kill the lights or something. I can show you some pictures and just talk about some of the considerations that we made. So every piece of steel on the bridge is doing something. It's carrying load, right? It's either being pulled, tension, compressed, compression, it's bending. It could be shearing, which is kind of a side-by-side motion, or it could be twisting, which is torsion. And so there are very few actual conditions like that we have to consider. So if you look at the towers being compressed, the cables and suspender rope are in tension because they're being pulled by the roadway, which wants to fall into the bay. It's pulling the cables. And in our case, usually in a suspension bridge, you have two huge concrete blocks, and you have two towers, right? And so you string the cable from one block to the other. So you have this force coming out of the anchor, kind of at a diagonal. The weight of the block counteracts the vertical component, and the shear between this block and the earth is what is counteracting the horizontal component. And that's all great if your soil conditions can handle a massive block. But if they can't, then you can do something like this, in which case we take the cable and we don't anchor it under a huge block, we anchor it back under the bridge deck itself. And so what happens is instead of that roadway deck just kind of hanging there for the ride, the cable is pulling it and compressing it. So it's working along with the cable. So this is the longest bridge of that type in the world. And also aesthetically, it kind of fits in with the other bridges in the area. And we considered the cable stay bridge which it still compresses the deck, but not as much. But I think aesthetically it wouldn't have fit in, and I think during the design competition, this was the choice.
Sure.
Okay. You know this stuff. This is okay. 2 major faults. You know that. This is 1989. I remember this. This is the old bridge. There was a collapse of one span, and the decision was made back then to replace rather than rebuild. So the entire project goes from Oakland to Riverwood Island. And so okay. And so this is your standard suspension bridge. You have those blocks at the end, which are anchoring the cable down. Now here we have the cable stay bridge, and those cables are coming directly to the deck. And they are putting the deck in somewhat of a compression, but not as much. Actually, the self-anchored bridge puts the deck in more compression. Here, the compression kind of builds up to a point, and in the self-anchored suspension bridge, you have the full force for the whole length. So, why don't you do a free body diagram for that? Also, think of it like this: you have an arch. The roadway wants to fall into the gorge there. The arch is being compressed and it's pushing against the walls of the canyon. What if you didn't have any walls, no canyon? You could put a cable from here to here. You can tighten that cable so that it resists that thrust, and then you can take that arch and pick it up and drop it wherever you want. And so, if there's an arch that crosses the highway in Berkeley, design like that. And if you take that and you flip it upside down, that's the self-anchored suspension. So, and this is what I kind of said. Step 1, step 2, you drape your cables, and that's the Golden Bay Bridge. And in the Bay Bridge, you have your tower with your piers, and then to support the cable, you need to have a deck. And here, you can string your cables and then hang your deck from your cables. Here, since the deck is working, since the cables, the deck has to go on to support the cables. So you need temporary supports to support the deck. So there's some wasted steel there. And it's actually one. So it's tied into this honeycomb of steel over this end. So engineers have to figure out, engineers are given the loads and they have to figure out the tension, the compression, the shear, the torsion. If it's being compressed and it's kind of long, it will buckle, so you have to consider buckling. In terms of earthquakes, we were given ground motions from seismologists, and basically you have displacements here that appear, which are given as a function of time. And if you consider your structure, you have, imagine you have a heavy block sitting on the table, and you shift that table quickly. Then you can pretty much tell the force between the block and the table by moving the second law. I think because then you know the acceleration, you know how much force there's going to be. But when you have a long structure kind of swaying on the wind, then you have to consider the stiffness of the structure. And also, as the structure begins to resist that load, maybe parts of it start to give way, and the structure itself resists that swaying. That's called damping. So you have to satisfy all of these conditions for every moment. You have a 20-second long ground motion, and you have to consider at each second what's happening. I'm going to just, if I had an hour, I could go through all of these things, but what I just talked about. here. We don't actually have one tower, we have 4 towers, and they're connected by these links, these beams right here, which don't really do anything. They're just sitting there. And they're made to be weaker than everything around them. So during a severe shaking, these beams are designed to fail. And that's pretty much a common way of participating in movement. You have the work that goes into failing those beams dissipates in movement. And so they're designed to be replaced. And even the ones that are high up. So there's a crane on the top of the tower that we're leaving there. So if there's an earthquake 50 years from now, you can just drop down and replace these beams. So by the way, they were tested full size. We ran some programs. By the way, none of this existed in 1936 when the original bridge was built. They just kind of assumed a horizontal force, which is about 1/10 of the force that the bridge will actually see, and been lucky since then. So this is kind of the cross section. This is what you're driving on. So you kind of have to build this considering the final condition. Like you have these suspender ropes coming either way. So we built this so that it arcs up by 2 inches, so that in the final condition it flattens out into the profile we want. We also, like I said, since the box is being compressed by the cable, it was built a foot longer than it had to be. So during the erection of the cable, the box was compressed. And we really nailed it. There were holes inside the box that had to line up with bolts on this pier, and they lined up further on. So that's what engineers have to consider. We have to think ahead to the final condition and kind of go backwards. So there it is being erected. It was fabricated in Shanghai and then shipped across the ocean in huge pieces, and they're very heavy. They're incredibly heavy. In fact, we had this huge crane in the day, maybe you noticed it, and it was pushed to about 95% of its capacity on the heaviest lift. So, by the way, this, you drive on top of these, and these are the segments, and they line up with the skyway there. This is basically a very thin steel plate making the perimeter. It's a little over a ½ inch thick. That plate has to line up with the adjacent plate to within about a 1/16 of an inch. And if they don't, then you're violating the welding code. And if they line up by, let's say, 3/8 of an inch, then you have a front page story in front of it. This is what happened. For a few spots, these boxes lined up by more, but they were outside of the welding code. So there are spots that people have to keep an eye on over time, but it's not a hazard, a danger to people. So, and oh, by the way, on the old bridge, there are cormorants, and nobody's allowed to touch them, so we have to be careful. And on the new bridge, we have these cormorant condos. They're basically like these shelves where the cormorants are going to be placed, actually. Or they might be forcibly moved there if they don't move there themselves. So, anyway, it was built in many places, 40 locations around the world. To be able to coordinate all of these things, basically, I'm a designer, so we design the bridge in its final condition. The contractor has to plan all this stuff. To coordinate all these tasks over 8 years in 40 locations around the world and a lot of locations here, and not lose money and keep everybody busy and working is that takes a lot of intelligence. So I'll just run through, this is what fabrications look like in China. There they are setting up the roadway decks. Here they are welding. And this is kind of a messy picture, but everything was fit up in China before it came over here, including the towers. Here's a couple of segments of the tower being fit up. And then just put them on a boat. And that's what we do. So I could show you one more slide. This might take about 3 minutes. But I think it's worth watching. Yeah, let's go. So this is once everything was in the client. Yeah, no problem. So, like I said, originally the deck was on these temporary structures. This just shows how the load was transferred to the cable. And it has a couple good close-up shots that are kind of cool. And so the contractors, engineers, they have to figure out how much is the cable going to be stretched by the load? How much are the suspender ropes going to be stretched by the load? And then they go back and they tell their fabricator how long to make the rope. And so they have to be right on it. And then the cable kind of twists as we're applying load to it. So we had to basically, there are these clamps on the cable where the suspender ropes come down. They have to be offset just right to offset that twist. So we've got these jacks here that are pushing down. As they push down, they're pulling down these rods, which are lowering the suspenders into place. And you can make a career just out of doing these 3D animations, because there's a lot of them. And as you apply the load to the suspenders, the girder comes off the temporary supports. See that? Flipping. And once the load is going through the ropes and not onto the support, you can get rid of all the temporary supports. And as you're compressing the box, these components, these bearings, are being pulled along with the box, and they're lining up with holes or bolts on the pier. And then we have this thing in the back that allows us to play with the cable even more if we need to, just adjusting the tension. So the contractors, engineers, they design all the temporary stuff, and we check it. And this is the coolest part, I think. The tower is going to lean forward because one span is longer than the other. To make up for that, the tower was pulled back towards the Island using cables that went from the top of the tower down to the island. It was pulled back a couple of feet, and then during that load transfer, it was pulled into its vertical position. So Okay, questions? Yeah.
Did you know you wanted to do bridges
No, not necessarily. I knew I wanted to do civil engineering, and you kind of, I don't know, life is like driving down a dark highway. Like you have your headlights on, you can only see 200 feet ahead, and so you make decisions based on those 200 feet, and then you keep going, and that's kind of the way it was for me. I didn't see 20 miles down the road, and you can't expect it to. Yeah.
Why make the bridge curved?
Why make it curved?
Yeah.
Well, we had to get out of the way of the old bridge. That's one thing. And the fact that it's curved was kind of it was a pain. It was a real thing because the curve was put on the suspension bridge. And by the way, I'll back up a little bit. There were a lot of political fights about where to put the bridge. Some people wanted to put it south of the old bridge, and the people who wanted to put it north eventually won. And that delayed the project by a couple of years back in the 90s. But basically, it does depend to some extent on the soil conditions and avoiding the old bridge and politics. So it's a mixture of those things. But putting that slight curve on the suspension bridge was a real thing. It's the way Caltrans laid out the geometry a long time ago. It had to, the last 50 meters of the bridge, if you're on it, you'll see it curve slightly. And that curve had to be done on a series of tiny kinks. And we had to reinforce the bridge at each one of those kinks. And so that was a pain. And also, on the west end, on the west span, you have one roadway on top of the other. On the east span, you're like this. Well, eventually you have to make some sort of divergence, right? You're parallel like this, and then you're on top of each other. That change, when you start getting away from parallel, that happens on the suspension bridge. And so what happens is you're kind of straight, and then you start doing this. We have these beams that connect eastbound and westbound. The last 3 beams that connect eastbound and westbound had to be kinked and warped to accommodate that geometry. It wasn't by much, we're talking inches. But if that transition could have been moved off the bridge, that would have made things a lot easier too. But there are rules about how quickly you can transition the highway to. Yeah.
So how are the holes drilled for the towers? In the actual, because you have to be underwater. So.
Yeah, let's see. Foundations, I didn't actually spend a lot of time on foundations. I know that, oh man, that's a good question. You basically have this, you basically drill piles down, and there are 13 piles altogether holding up the tower. And they're extremely long, probably, they go down to bedrock, but they might be in the neighborhood of 200 feet long. And so they're kind of, they're drilled into the, let's see if I can remember, forgive me, but they're able to go, I believe what happens is, they get down to bedrock, and then you have to drill. It was just something I grew up around. I grew up in New York, and so their bridges are everywhere. And it seemed cool, just at the time, to be able to go out once a week and climb up on bridges and check out issues and do some design work. And then after that, my firm was one of the firms that was involved in it. So. And bridges are kind of cool if you're working on a signature span, a unique bridge. But as you can imagine, there are thousands of bridges, and a lot of them are kind of cookie cutter bridges. So you don't want to have to reinvent the wheel every time you build a bridge. So if you work for Caltrans, they can take designs off the shelf. But for bridges like this, they need to get specialty firms to help. And so again, it was just like, I didn't have a plan when I was in high school. Yeah.
So if you work on constructing a new bridge, you also work on deconstructing the old one?
I don't, but some people I worked with do, but there's a lot of engineering that goes into that. Because every member on that bridge is either in tension or compression. And every time you cut it, you're releasing that tension or compression that has to go somewhere. So at every stage in construction, you have to analyze where all your forces are going. And actually, in a lot of cases, you have to reinforce certain parts of the structure before you can demolish others. Yeah.
So you said you didn't really have a plan out of high school. Do you still go into college doing like civil engineering?
Yeah, I was civil engineering from day one, and I thought about quitting a couple times, but no, I didn't. So yeah.
Did you do any internships or study abroad in college?
No, I didn't. One piece of advice I would give you is just like right now, if you can take AP tests and get some college credit, it gives you a lot more academic freedom in college. Because if you're an engineer, things are very structured for 4 years. And if you have the basics out of the way, if you have physics and chemistry and calculus done, you don't have to take those classes. You have the option to take more interesting stuff, do research. You can maybe study abroad. You can graduate in 3 years maybe, or 4 with a master's. So that's something I didn't know at the time, but my program was pretty structured, and so my 4 years were book solid. Yeah. What's in it? That covers, that's the engineering training exam. It covers basically electrical circuits, thermodynamics, it covers math, it covers chemistry and physics, it covers some basic structural mechanics, but it covers like fluid mechanics too. It covers a